So we are trying to calculate, therefore, the sorry, the so x will be equals to so this is your small x which is the signal. Okay, so this is the small x which is the signal, and then I compute that the this is your 512 point FFT. I try to calculate. So I give here, now this is your amplitude spectrum, capital X, which is basically the Fourier transform FFT in MATLAB. Of course, in case of your Python, it might be a different word. That's fine. So we give the time series data X, which we have generated here from the rectangular pulse, and then also the NFFT. So that is the number of data points you like to use for the calculations, right? So that means it will generate 512 points spectral data. It's clear? Okay, so 512 point spectral data, it will be created, and whenever you take the data, 512 point spectral data has been created. Please remember, this data is in a complex form. So that means it has a real part as well as the imaginary part, because the Fourier transform is a complex function. So you will be getting a complex data. Okay. Now from that complex data, 512 point complex data, you just throw away half of them. So just throw away half of them. So that is what we are trying to do. It is from 1 to NFFT divided by 2. So that data you take, right? So only half of the Fourier transform things you take it there, and you will be take the that your MX, the magnitude of this one you need to calculate. So that will be map the absolute values of the X value. So that means you are trying to calculate amplitude spectra. So absolute value means you take the real component square plus imaginary component square. That will be the root over. So that's the absolute values you are basically trying to calculate, right? So it's basically now the real values. Sure. Now this is your time values, whatever you have given here. So this is your time series data from your things. So now you have to define what is my frequency intervals, right? So the frequency interval will go from because you have thrown away half of the data, so or half NFFT by 2 you have thrown away. So now you would have a 0 to NFFT by 2 minus 1, right? So basically earlier you have a 0 to N minus 1. So now you have a 0 to NFFT by 2 minus 1. And then this will be equals to your Fs will be the NFFT. So Fs means your whatever your sampling frequency you have used, 150 divided by the number of, that means the 512. So that you have to multiply it, right? So that means first value Fs NFT multiplied by 0. So then that will be equals to your 0. So first Fourier transform first value will be always equals to 0, right? And then it will be equals to 1, means Fs NFFT. So Fs is the sampling divided by N FFT. So that's your first value. Let's see that Fs equals to 150. So 150 divided by 512, right? With the multiply the 1, right? Next value will be the 2 into 150 divided by 512. So in this way it will be going. So that means that will be the Fs, that will be the F value, and then you can plot with your T and X and do these things, right? So you can plot the T and X is the time series. So this is your this, and then F and MX. And MX is the absolute value. So that you can plot, and that is your the power series of this one, right? So this is your this is your absolute value. So this is your only the absolute part. So it's only the real and imaginary. So so this is your basically it's a power. Now, if you have the recorded data, as I have given it to you yesterday, so you first calculate the amplitude part. So that means the first part is the time, second column is the acceleration data. So this is your second column data. The first column is the time for any data sets, if it's time data. So then you calculate the time interval. So that means this is basically your delta t, time difference you calculate. So that means what is your sampling of the time. So that is, you can calculate it. And then you take your length of the data. So because you have, say, something around 24,000 of the data. So 24,000 data points. So 24,000 data points multiplied 0.005, say, suppose if it is a 200 samples per second. So that meaning of data you have. So you take that data and then use this command to calculate the next power of 2. So that means if you have if your data points is say 1408, and then next power of 2 we need to calculate, say suppose this will be then 2 to the power of next power of 2 will be basically something around 2408. So that you need to calculate what is the next power of 2, right? So that you can calculate, and if you want, you can also pad the data if you like to use, but the MATLAB will automatically do that. You need not to do it specifically. They will calculate that then the next part, and then you can calculate the absolute FFT, and then you can compute your DF value. So this is your frequency difference, and then compute your this plot, and then calculate your Fourier transform, just like whatever I have shown it to be before. So this data, so you can calculate that numbers. So now there are two things. First of all, in case of your seismological world, we always try to put it the amplitude value in a log scale, and frequency value also in a log scale, right? So whenever we plot it, instead of a plot, you always use log scale. So that means both are in a log, and then if you can plot it both in a log, then the acceleration data looks like always like this. So that means you will see it here when there is you can see it here. The pictures will be like this. You'll be seeing it that there is a case like this. Then there is it will rise and then it will fall. In between, there is a flat part, right? So this is what we call it as a corner frequency, FC, and this is what we call it as a F max or FM values. And then after FM, it will go gradually decreases. So this is your acceleration spectra. So acceleration spectra, I told you, if it is a centimeter per second things, right? Because centimeter is a centimeter second square. Centimeter per second is the acceleration values, and then multiplied with a dt, it will be centimeter per second things, right? So the acceleration spectra always looks like this. So if you take the acceleration spectra and divide with as I said, that it is a j omega square, then what you get is a d omega, or the displacement spectra, right? So then you will be getting the displacement spectra. So acceleration spectra divided by j omega square but the j square means it's a -1, right? So then j square, j is the imaginary number, and that square equals to -1. So it's the minus of a f by omega square. That will be equals to your displacement spectra. Now, if you see the displacement spectra, then the displacement spectra will be looks like this. So if it is a log scale in the frequency, and then this is your amplitude, okay, the displacement spectra will be looks like this. So the type of the displacement spectra will be like this, and then this will be the frequency of the this your fc, which is coming it here. This fc will be here, right? So that is your corner frequency of the displacement spectra, and this is what we call it as a low frequency level. So the low frequency amplitude level, amplitude level, that will be used to calculate the M0 values. What is the significance constant? Is the physical significance probably frequency? The frequency, the corner frequency is the frequency at which the I told you that when he hears that a pulse, it will be like this. So when there is a rise time, right? So that rise time is basically indicative of this one. So TR, if it is a tau R, which is the rise time, so that will be equals to 1 by of your Fc. Right? It's related with the parts of fault rise. So that means from there, how quickly it comes and gets stabilized, that time rise is basically related with the Fc. Okay. So this is your so I might be giving you a try or write a Fourier transform in your afternoon class with a very, when they define a signal like this way, say 5 sine 2 pi 4 into t plus 10 sine 2 pi 8 into t plus 12 sine 2 pi 10 into t. So make all the signal together, right? So these are all sine pulse. Make all the signal together so that they have a different amplitude. 5, 10 might be the this is the 12, and they have a different frequencies, right? So they have a different frequency of 4 hertz, might be the 8 hertz, might be the 10 hertz. So these frequencies are there, and you are mixing it up all the signals, and then take the Fourier transform of this y and see whether your pulses or your spectral value coming at after you do the Fourier transform, it should come at around 4 hertz, at around 8 hertz, at around 10 hertz or not. And if these amplitudes are basically this, when it will be equals to 12, this will be equals to 10, and this will be equals to 5 or not. So if it is, then your Fourier transform algorithm is correct. So you can use now for any signal, you can give it to them, and then it will calculate, right? So you there's a signal, and then make a sample so that it should have a.
How does we extend that the algorithm is correct?
Something this is the kind of signal, and if you're reading this about just peak on at the 2 hertz, 4 hertz, and 8 hertz, so then it's fine. Then it gives you that whatever you wanted. So you just give your proper sampling and the duration of the sample, you can make it from 0 to 1 second. That's fine. Make it a 0 to 1 second signal and sample it in a proper way, and then you can calculate, right? So that will be helpful to you to follow the things. Okay.
Sir, really where to, after doing SSD, which frequencies are dominant in which parameters?
Yeah, it is happen. I think it was happen. Then say suppose here I will be saying that 10 hertz is dominating because the 10 hertz amplitude is 12, right? So that means that frequency is the dominating frequency. So that you have to do, and then only you can find it out. After you do the Fourier transform, then only you can find it out. Okay? Does it make sense to everybody? Okay. Now, what we need to know is basically the sampling frequency and the Nyquist frequency. I told you last time that that the sampling frequency is a frequency when you are sampling the data, right? So whenever you are, and that is fixed for your recording stations, you fix it. That okay, I require this much of frequency, so I will keep that. So that means if we sample the frequency at a 200 samples per second, so that means 200 hertz. 200 samples per second means it's basically 200 hertz. So 200 samples per second means it's basically 0.005 second interval you are trying to calculate, right? So therefore you are interested in you are sampling it at a 200 hertz. So you can only get the maximum frequency you can get is only 100 hertz, not more than that. So if you try to now extract a 125 hertz frequency from these 200 samples per second, then you have done but you will be ended up with some problem because 125 hertz is basically the replica of whatever you are seeing it at 25 hertz. So so similarly, you need to be careful about the sampling frequency. So the Nyquist frequency, if it is a sample frequency, is basically 200 samples per second or 200 hertz, then your Nyquist frequency will be half of this one. So that means this will be always 100 hertz. So that is the maximum information you can get. So if you need to have a 200 hertz type of information from your spectral data, then you have to sample it more than the sampling frequency of 200 hertz. So that means might be the 400 hertz sampling you need to use. So that you have to set it up before, because otherwise, even if you cry, nobody will be helping you because the data is gone. You have not sampled it, so it's gone. You cannot get it back. Okay, so that you always keep it in mind that you have to have a sample in a proper value in order to get the requisite type of frequency information you wanted. Okay, so that's the part. So this is your sampling frequency is 1 by t. So that means that this will be equals to your total time. So that you find it out. And if you do not have a proper, let me see, I can show you this one. So there is a little bit mathematics. You can always see that. So if your sample is a Nyquist frequency is this one, then it is a Qn to Qn, and then this is your QS and then 3QS and all these things. So if your sampling is more than your 2 times of Nyquist frequency. So that means Nyquist is say 100. So 2 times of 100, your sample is more than that, more than 200 hertz. So then your signal, which is like this way, you will be getting a replica like this. But if your sample is basically less than that, this one, I don't know why it's a 2Q comes, but then you will be seeing that your signal will be just get aliasing with the nearest frequency, and that will not give you the proper proper information of your time domain frequency content, right? So basically that will be difficult. So what we need to do after you sample it, we will be putting a low pass filter, and that will filter out all the high frequency side, and we will be taking out this one to calculate the Fourier transform. If we have a issue with the if you like to retrieve your data, so you have to have the sample. If the sample frequency is this, then we can put a low pass filter and take this data out, because this is our Fourier transform actual data. The others are not, right? So, but if you have a less than this one, it will be all be superimposed, and that is what we call it as a aliasing effect. That is what is known as a aliasing effect. Aliasing effect. So that effect we need to minimize. Okay. So keep the Nyquist frequency proper, and so if you lower the sample rate, but if you're lowering the sample rate, then it will be reducing the Nyquist frequency. So that means it reduces the maximum measurable frequency, but it does not affect any frequency resolution. So the frequency resolution depends upon the number of time the data you use. So that does not affect your frequency of resolution, but it will be the maximum frequency that will be effect. So if you have if you change the sampling duration, so if the duration of sample is being changed, so reducing the sampling duration, it will be the lowers the frequency resolution. So that will happen, but it does not affect the range of the frequency you are measuring. So there are two things: either you can change the sampling duration, or you can change the sample rate, right? So that's the two main part we need to be careful about, and before we take this one. Okay. So now the another main part is the filtering part. So why you need the filtering? The filtering is needed to remove some of the unwanted noise, right? So some of the unwanted noise we need to remove, or unwanted frequency values we need to remove in order to do so that's why we do the filtering. So what we are interested in is some frequency interval. So beyond that, or might be the less than that, we are not interested. So based on that, we have several type of frequency, several type of filtering. Now this filtering is done in the frequency domain. So therefore, we have to understand that what are the frequencies I need to use. So first of all, we are doing the filtering operation in frequency domain. So that means we calculate the spectra and then do the frequency domain frequency domain filtering. Right? So it is a frequency domain filtering, and we are doing it three main type of filter. It is a high pass, low pass, and then there is a band pass. Right? So high pass filter means it filters the So high pass means what? High pitch low frequency cut. So that means it will be 0 here, and it will be, the gate will be open for the high frequency part, right? So that is your H or the high frequency signal, right? So it will go like this way. Then there is a low pass means it's a low frequency get passed, so the sectority on the filter to be like, so the gating will be means, right? So that the people to your film, right? So that's this time, and then there's the band pass. So band pass means something so John. The same. So is such that it is continuous band we like to move, and this band will pass both the sides. It will be blocked, right? And then there is a band reject. Now, what is the band reject?
Yeah, let's see, privilege, but are they done the rest?
Usually, you can see that sometimes if you are trying to take the wheelbarrow in a very high voltage line is present, that high voltage line is or this is a part of the sum. This will be the opposite type, right? So this will be like this way. So that means both the sides, both the band is there. Then this can be also moved as a special filter like this. So we like to do a filtering like this. This is called notch filter. So notch filter means a particular frequency, as I said, suppose a 50 hertz signal we need to remove, because that will be always interfering with our recorded data, particularly if you are trying to calculate the electromagnetic data, then the 50 hertz frequency will always hampers the things. Or sometimes if you are trying to record it inside the house, then the frequency of this electric power, because it's a electromagnetic sensor. So basically that will also affect. So sometimes we have to remove that particular frequencies. So these are the digital filtering we need to do. Okay. Now, so in case of your digital filtering, first of all, you need to understand, and that is the note I was trying to do today, Monday morning, and it is all gone. I cannot save it somewhere or other. Now let's see. We have two things we need to understand. Whenever you do the filtering, there will be some terminology. The first terminology is that it's a causal and acausal, or the non-causal. Now, do you know what is a causal filtering and what is a non-causal filtering?
The thing I'm saying to offset from your elaboration is equal to 0 in the policies. So I was saying, I just like, our part of the signal side below 0 bastard. 0 time. Yeah, it's simple. The things we process on what is the part of the filtering now, what is the non-causal pattern, kind of well, that I do not make in the trend. I was setting usage, it takes on quality damage. Okay. I'm supposing that I on the offset was prepared.
Yeah, sure. The what we're doing.
The
The precious signal.
signal, which are the current as well as the previous one. Okay, so they will take that, and that filter response will be depends on the past history of the signal as well as the present one. But the non-causal one, it also takes the future one. So that's a non-causal. So past and present and also the future signal things, they will be doing the thing. So that's a non-causal part. So that's the two difference you need to understand. Most of our filter is actually a causal filter. We are filter response depends upon the, at a particular point, whatever the filter response, it depends upon whatever the signal at this point and also whatever the a little bit past. Okay. Next filter we always talk about, it's a IIR filter and then FIR filter. So what is your IIR filter? Infinite impulse response filter and finite impulse response filter. So electronics. Good. So now I want you the answer from me. So what is your IIR filter and what is your FIR filter?
Student boss, student boss, there's kind of, I had that, student boss, student boss, so about teacher. Okay. And kept on with who's by night, I will do this other civil. And there is, if it is paper, she will feel it at his plant.
If you put an impulse value, then that if you put in a filter, okay, let's see like this way. If I say, suppose this is the filter, right? So this filter has a response. Now, how do you calculate the response of a filter? What we do, we put a unit impulse to the filter input, right? And then if you give the unit impulse, then whatever it will be providing in the as the output, that is what we call it as a, that is what we call it as the impulse response of this filter. Because this filter is a black box. I do not know what is there. So I give a unit pulse, and then I like to see what are the output of this filter. So that is what we call it as a impulse response of the filter, because I give a impulse, so that is the response of the filter. So that is your impulse response of the filter. Now this impulse response of the filter is important because, so now I know, let's see, this is a 2, 5 and say suppose 3. So this filter has an impulse response 2, 5, 3. Now if I have this filter and then I give now a real input, then that will be convolved with your 2, 5 and 3, right? So that will be convolved with your 2, 5, 3 and it will produce some output, right? So that is your convolution product and that will produce the output, and that is your output for this signal or this filtered signal, right? So that will be the output of the filtered signal if you can put that text. Now, impulse or FIR or the finite impulse response, as the word suggests, it's a finite impulse. So that means if you put an impulse here, it will be giving you some finite values. It will not infinitely, it will not go. Okay, so this is called your finite impulse response. And if it is a infinite impulse response, so that means if you give a unit impulse, then it will be produces a trail of impulse, which is basically called our infinite in range, right? So that will be calling as a IIR or infinite impulse response, right? So that's the two definitions, and that are the two types of
So what you told, into infinite thing for suppose like whatever signal we are giving, that is repeating itself. But I believe
Huh?
whatever signal we are giving in infinite response, so it's replicating itself up to the infinite.
Taking it out. No, it is the signal will be the output signal will have a trail of infinitely ranged in the output. So that means it will have
Frequency component is so and it can take it in the same.
so basically into the target infinite infinite time length or infinite length of the response in the output. So that will be getting as a IIR. So, but if it is a finite length of response from a filter, then we call it as a FIR filters. Okay. Now, let's try to understand that which one we will be using. So we will be using mostly the our most common field in our digital signal processing for our say suppose the geophysical data, for exploration data, for any others. We all use mostly the IIR filters, right? So that IIR filters are basically we have all the, if you can say, the Butterworth filter, your Chebyshev filter, Bessel filters. These are all IIR type of filters, right? Okay. So now, first of all, we need to understand that what I need to tell. Yeah. So the filter always have some two things. One is we call it as a pass band.
Yeah.
So where the signal is allowed to pass, and then there is a stop band where the frequency will be cut, right? So that means that frequency will not allow to do. Now, ideally, the ideal filter, it will be like this. So that means it will be pictures like this way. So that means that is what I draw. That is your FL or FH or whatever like this. But it will not like that way. So there is such a little bit slope is there. It gradually depends or gradually goes to the stop band from the pass band, right? So this is what we call it as a slope of the filter. So this is your slope of the filter. Now this slope of the filter depends on what we call it as a order of the filter. So this is called the filter order. Okay, order of a filter. Does it make sense? So this is your filter order. Now there are a lot of compromise. The compromise means it is either we want the pass band to be little bit has a ripple, that's okay, but your decay has to be sharp. We have that type of filter, but in other filter, the pass band is more or less stable, but the decay part will have to adjust. Okay, so that way it can be, there will be some sort of a leaking in between this part, because if there is a more this way, then there will be some signal will be leaking in between this value and these values, right? So this definition is required. So this is what we call it as a corner frequency. So the frequency or the cutoff frequency. So this frequency is basically we like to cut, and this cut will be, we call it as some sort of a, not a very sharp peak, but a peak like this way. Okay. So this is this is actually what we call it as a 3 dB loss. So that means it is a or minus 3.01 dB. Now what is dB?
Yes, it's or basic English thing, or that I say, but that is the actual. It's we like in the side that like rather than another song listening songs against you can just and staying in your regular about that indicates turning dark and that's that very beginning of the picture also. And that I'm going to give one of the pizza the nutrients put. Nobody really put to it. So you can the signal so decimal
The decimal,
Bias.
so you need to bias
This there.
in this and
so decimal is it provides to, but I think that basically the bill is the, say suppose two power level P1 and P2. How much is the P1 with respect to the P2? So that if you need to calculate, then the bill has suggested to take it as a 10 log of P1 divided by P2, right? So that is what we call it as a decibel, right? So that is the P1 by P2 is the bill. So then multiply with the 10. So then it is called decibel. So that's a decibel unit or the dB unit. Now, if you P is the power, if you take it to the amplitude, then it will be the 10 of log. Then this is your power means A1 square by A2 square, or might be 10 of log A1 by A2. So then if you make it a square, then it will be the 20 log amplitude by M, right? So that is your 20 log amplitude by amplitude, right? Okay, so you can see this frequency. So this frequency is what? This frequency is? This frequency is 10, right? 10. And this frequency is?
get ready.
Say 1. So from 1 to 10, it has 0. These things has been drawn by how much? Or dropped by how much? Huh? In a 10 frequency range, how much it is dropped?
And so it was the minute Christ done. You know,
20. That's the piece of 20, this 708, it has been dropped, right? So this slope, we call it as a 20 dB per decade. Decade means per 10 times. So 20 dB per decade. Now, can you calculate from this picture what is its dB per octave? So 20 dB per decade it is equals to how much dB per octave? So pre that we're I could take in the weight. I have 16
System.
the what we go with that's 16 for me. And like the so I was it was and was I was persistent on compare things but I so and this to up so important is that helping insurance senses
it one decade. One decade will be what is when you have frequency you station. So that will be the 10 times of that frequency, right? So F2 will be equals to then the 10 times of F1. If F1 is 1, then F2 will be the 10, right? So that's your decade. Decade means 10 times of your original one. So octave means 1 octave means it is basically the 2 times of the original one. So F2 will be the 2 times of original one, right? So you see that when the algorithm of maybe significant until 1, and that means that your 10 into F1 will be equals to 2 to the power n into F1, right? So that is your, how many octave will fit it here? So F1 is get cancelled. So 10 into 2 to the power n. So this is n will be equals to log 2 into 10. Now what is the log 2 into 10? Can you tell me what is the log 2 into 10? 3.3. Huh? 3.32. Okay. So n equals to 3.32, right? So n equals to 3.32. So then you can calculate that that your 20 dB per decade and the dB per octave will be equals to how much? Simple. About 6. Approximately 6, right? So that will be equals to 20 into 20 into 20 dB into 3.32, right? Right. Huh? Yeah. So 20 dB into so dB per octave, when it will be equals to 6.02, right? 6.02 dB per octave. So I can give the definition 20 dB per of past decade or might be that 20 dB. So this is not slope. So you can have it. Everything will be depend on the slope by this numbers, right? So that this slope will be necessarily basically interested in. So if your n equals to so we are basically what we try to use in our mostly in our data is the Butterworth filter, right? So Butterworth filter is a low pass Butterworth filter or might be the high pass Butterworth filter. If you can see that, so omega, if it is less than omega 0, then this will be always the magnitude. So let's see. This is the case. This is the very right. This is the very. So this one. So this is your mod omega. Means both sides. This will be plus 1 and minus. This is the minus and plus. If it is a less than omega, then it is a 1, and then on outside that, it is the 0, right? So this is your simple most filter, right? So that is your simple filter, and so this filter we call it also or we can call it as a high pass filter, because this frequency is a pass on this side, or might be this will be on the minus. This will be going like this way. So this one be we call it as a, so this is your low pass filter, and because this frequency, if it is the positive frequency, this frequency will pass, and his brother is always the high frequency part. So that means this frequency is blocked and this frequency are being passed, right? So that is your HH will be equals to 1 by HL omega. So that means this will be equals to this one and this one, right? So now let's see. Don't worry about this one. So let us see. Okay. Now the next another thing, it is called, there is another type of filter you will be encountered. It is called zero phase. Now, what do you mean by a zero phase filter? It's time, you see, it's time to zero.
You know, it would be involves what you know, perspective and double discussion. Yeah, basically. But it is essential. It is restricted. Yeah, that's what I mean. It's what. He gave back to me, so I tired on the same visualize people say to the zero like working. They're staying here, standing about the guy in the distance and the big ass teams in Indo. You might say all the countries have the same thing. Well, and found the winners. I mean, in zero, that is. So that was art. The study, I study is that the T is equal to zero. All the components will have the like indicators in the air bicycle. Okay. So I'm more analysis. Okay, and so what are you starting up money working but how he's seeking a very important time. The person that I'm usually with say that. What they will align those or it's get out maybe see like the you could like the new what's it took us. I mean student means shift me it goes to there's all look at this. So got this on play no this. The person working and where I'm just gonna shoot. Well, we're still saying needs that will keep the signal are non-digit engaged with respect to the input signal. So that means whatever is the input signal, the output signal will come in the same way. So that means they will be in the same phase. So that means the phase here means just like this. Say you have seen the long distance dash in your suppose 800 meter or or might be the 400-meter case in your run competition. You will see the peoples are at a different point at the initial things, right? Because they are not start from the same point because somebody has to go for a small circle and somebody has to cover the big circle. So they are at a different points. So that means they have a delayed in their starting points, right? Or somebody is in a little bit delay with the things. So that means they are at a different phase. They are at a different phase. So, but here we call it as a zero phase. So what he was trying to mention that all are at the same points. Yes, all are at the same point. But then in case of a filter, that is what we try to call that whenever the input you are giving it and output you are receiving, these things are not get delayed. So that means that the time where you are getting the input, you are getting the same as an output in the other point. So that the other points or the filter points are not get delayed. It is called zero phase type of filters. And zero phase causal filter. So that means it output depends on the current input and the past input, but not on the future inputs, right? So that is what it is called the causal filter. So we have a zero phase causal filters, and that has to be multiplied, and we are using mostly in our day-to-day work when you can use the different filter setting also, but mostly we are using a Butterworth type of filter because Butterworth filter has a zero stop band. So that means at the stop, if you can see it here, the stop band is here, and then it will be decayed like this, right? So if it is a n equals to 1, then it has a longer decay. But if it is a n or the order of the filter, n equals to 4, then what will happen? It will have a decay like this. If you have a n equals to 9, then your decay will be much more sharp. If you have when n equals to 16, then it will be a straight down decay. So this is your different
order of the Butterworth filter, and that depends upon these parameters, right? So that depends upon this parameter. N is called order of the filter, and this is your cutoff frequency, what you need to choose. So this is your omega value. This is your omega C is the cutoff frequency, and then this is your order of the filter. So this is what we call it as a Butterworth filter. So this is all, whatever I am showing it here, these are all low pass, and also the Butterworth is a zero phase filter, right? So we are using a zero phase low pass filter. Typically n equals to 2 to n equals to 4 we mostly use, okay? Because otherwise, if you have this type of things, it can be used, but then sometimes the filter becomes unstable. So you need to be very careful about if you are using higher order values. So typically the n equals to 2 to n equals to 4 are mostly the somebody can, if you take the filter setting properly, then somebody might be n equals to 8 also, but not more than that. Okay? 8. Okay, so just a minute. So so basically you can see this that if you are different filter should today afternoon the class we will be doing some of the different, say suppose the filtering operations as well as the Fourier transform, and also the ground motion parameters estimation. So let us see how much we can do it today. These are but everybody should come with the MATLAB or might be the Python toolbox, okay, so that it can be done.